Hello friends, today we are going to discuss the basic idea regarding the applications of paleontological data in paleoecology and a brief idea of paleogeography. The information given by the fossils is not only significant for determining the age of the rock, but also the idea concerning paleobiology is useful. The taxa used for paleoecological interpretations should essentially be benthic in order to get the most probable ecology. The Earth is a dynamic planet wherein every piece of crust is under constant movement and has remained so since Archean. Applying the principle of uniformity, this movement of crust has changed the paleogeography dramatically on geological timescale. The study of paleogeography is therefore extremely fascinating. The paleoautoecology of an extinct organism may be taken broadly to equate to its mode of life. Of course, there are aspects of fossil paleoautoecologies for which there is very little hope of being able to reconstruct. For example, arguments made from the homology with living relatives and analogy from organisms with apparently similar adaptations from trace fossils or from models of fossils can be used. Still have extant representatives, much can be learned by applying knowledge about living taxa, using principles of homology. Clearly, any have lived in the same way are tenuous. Interpretations of the modes of life of most fossil bivalve mollusks is relatively straightforward. Several features of bivalves make these organisms ideal for paleoecological reconstruction. First, modern bivalves are most diverse both in terms of taxonomic units and in life habits than ever before in their 500 million year evolutionary history, meaning that the interpretations can be based on a wide range of possible models. Second, a wide variety, for example, oysters, scallops, mussels and clams is of great commercial interest, and consequently their biologies have been studied intensively. Third, it is well demonstrated that bivalve shell morphology and the life habits are intimately related. Several aspects of its morphology can be used to interpret the paleoecology of this animal, based on comparison with a living bivalve of the same family. The oldest part of the shell, close to the umbo, is a regular scallop shape and shows the morphological features associated with attachment to a hard substrate by byssal threads spun by the foot. The surrounding section lateral growth of the shell is highly irregular, and its form varies among individuals because at this size the bivalve began to cement to the seafloor and modified its shape to suit the substrate. Experimental evidence has shown that cementation in bivalves is a good defense against predators. Clearly, some caution is required in using modern organisms to interpret the paleoecology of extinct fossils, even when they are closely related. Some organisms have undergone a major shift in aspects of their life habits over their evolutionary history. For example, monoplacophorans, a primitive cap-like molluscans class, are known from a variety of shallow marine sediments from the lower Paleozoic, apparently living in communities alongside brachiopods and trilobites, then apparently disappear from the fossil record during the Devonian and were presumed extinct until the celebrated rediscovery of Neoplena during a dredging of the deep water, that is more than 3,500 meters off the coast of Mexico during the Danish-led Galatea expedition in 1952. However, it would clearly be inappropriate to reconstruct the paleoecology of the Paleozoic forms based solely on our understanding of the biology of Neopilina. Presumably during the Upper Paleozoic, monoplacophorans were forced perhaps by the competition or predation pressure into deep water refuges that are not represented in the sedimentary record. Other Paleozoic taxa that was important and widespread in shelf communities such as brachiopods and stalactinoids are postulated by some also to have been driven into refugia. These examples clearly demonstrate the need to use several lines of evidence when reconstructing paleoecology, and most importantly, not to divorce the study of fossils from their lithological context. What happens when there are no convenient living homologues? In such cases, the paleoecologist must use more imaginative approaches. Trilobites became extinct by the close of Paleozoic, although much may be gleaned of their paleobiology by homology and by analogy with other arthropod groups, such as understanding their molting and likely internal anatomy. It is believed that the trilobites exploited a wide range of life habits, although most were benthic, others were pelagic or nectonic. Some, for example calamine, are interpreted as having been voracious predators, whereas others were thought to have been filter feeders or deposit feeders. The lines of evidence used to elucidate these different paleoecological details are varied. Much is reliant on the detailed studies of functional morphology, but evidence from trace fossils, including some that show evidence of trilobites striking worms, experimental modeling have also played a role. An interesting example is the interpretation of the lower Paleozoic olinalids as possible chemosymbionts is an elegant study by Richards Forte. Using a combination of evidence based on the functional morphology of the family, principally the large number and wide nature of the thoracic segments and degenerate hypostome, the lithological evidence that olinalids tended to inhabit sulfur-rich unbioturbated black shales, and by analogy with totally unrelated modern chemosymbiotic organisms such as leucinid bivalves. Forte suggested that these trilobites might well have harbored sulfate-reducing bacteria on their gills, which allowed them to live in difficult oxygen-poor environments. When living relatives and even good analogues are absent, more conventional or more unconventional approaches can be taken in the study of the fossil mode of life. Graptoloids were a significant group of the macrozooplankton living in the Ordovician to mid-Devonian open seas. They have very remote living relatives, the pterobranchs, but their benthic encrusting mode of life makes direct comparisons unrealistic. Instead, work has concentrated on the response of graptoloid shapes to seawater, which had the same properties in the lower Paleozoic as it does now. Physical and computer-derived models show that both the overall colony shape and its detailed morphology would have had important consequences for the behavior of the species in water. Colonies were designed to rotate during movement, thereby increasing the volumes of water that could be sampled. Flow of water was directed into the thecal apertures where the zooids lived by an arrangement of spines, hoods or hooks in many species. A standard orientation relative to the dominant direction of water flow was maintained by structures such as the virgula and virgula, arrayed at that proximal and distal ends of the colony. Understanding the physical effects of the adaptations shown by fossils allow inferences about life habits to be made, for example, concerning the likely feeding position of the zooids and the sampling requirements that contained or conditioned their fitness and hence evolution. Ecologists define a community as a recurring group of taxa in fixed proportions that live together in a particular habitat. The focus of interest is in which population of single species or different taxa interact and the manner in which resources within that habitat are shared between the different groups. Ecological studies can be well founded on quantitative analyses based on direct observations. Paleoecologists, however, are faced with a number of problems and must use less direct methods. First, a high proportion of any community may be soft-bodied or weakly skeletonized such that they are unlikely to be preserved in the fossil record. It is estimated that more than 70% of the modern taxa fall into this category, and the Middle Cambrian Burgess Shale provides a statutory or salutary lesson showing the wealth of poorly or unskeletonized organisms such as worms and arthropods not usually preserved in contemporary deposits. Second, relatively few organisms are preserved in the life position, and many may have been transported far from their original habitats. As a result, the paleoecologist must reconsider or consider whether the group of fossils being studied is autochthonous, that is, preserved in the life position. Parautochthonous, that is, the elements are distributed and disarticulated, but the fossils are not necessarily far removed from their origins. Or allochthonous, that is, organisms from different habitats have been swept together before drawing any conclusions. Third, even if a group of fossils is considered autochthonous, it has to be recognized that any bed or even bedding plane assemblage is going to be time averaged, and it will thus contain a sample of individuals that lived on that site over many centuries or even thousands of years. In this way, individuals of the same species but of very different generations may be found next to one another, or taxa that lived in successive communities on that site may appear to have coexisted. As a result of these complications, paleoecologists prefer to use the term assemblage rather than community. In addition, the soft body components of the original communities are seldom found fossilized. If similar assemblages are found to occur widely, either geographically or temporally, this provides a good indication that they are a real ecological phenomenon, and these are given the name of associations. Investigating fossil populations. Populations of organisms are sensitive to characteristics of the environment and can be studied in two main ways: by the examination of life strategy and through survivorship analysis. Two extreme life strategies, commonly termed R and K, are derived from the logistic equation that states that the number of individuals N in a population will be a function of the reproductive rate R modified by the closeness of the number of individuals to the total number that can be supported by an environment, that is the carrying capacity, or K. The R strategies, species dependent heavily on high rates of reproduction, often breed early, that is at small size, and may die after breeding. They generally invest little in the care of the offsprings but have many offsprings at once. This strategy is characteristic of the unstable environments in which the carrying capacity varies significantly over short time scales. The K strategist species breed late, often bearing single young over whom care is expended. Individuals often live for a considerable time even after breeding has ceased. This strategy is typical of stable environments in which the carrying capacity is highly predictable. Although these two descriptions are extremes and most organisms show a mixture of R and K features, the generalizations have great use in making first-level interpretation of the population dynamics. Survivorship analysis is a complementary tool for use in the examination of fossil populations. The number of survivors of each age group of a population is plotted on a logarithmic scale as a function of the age. In fossil populations, the number of survivors can be inferred if the bedding plane is time averaged or can be observed if a mass mortality of a single group reduced the association. Most survivorship curves fall into three distinct categories, though variations exist and organisms with very different life habits at different stages of their lives may show composite patterns. In cases in which the high infant mortality occurs, as might be seen for example in fish stocks, the survivorship curve will be concave. In environments in which there is an equal risk of mortality at any age, the survivorship curve will be straight. The classic example of this type of curve is that of the garden birds. Paleontological examples are found especially in extreme environments in which mortality is generated by frequent, unpredictable and unselective events. In more stable environments, mortality rate is low initially but increases with age after a certain point, producing a convex survivorship curve. In these cases, the organism can be fit enough to survive the variations seen in their environment, but this characteristic is reduced later in life through the illness or gerontic effects. The competitive exclusion principle suggests that two species that have exactly the same requirement cannot exist together within a habitat. Where two species do appear to have the same requirements, one will be prevented from maintaining a viable population by the success of the other, or one will be forced to adapt in order to use slightly different resources. The latter strategy may involve character displacement, for example, modifications of the filter feeding apparatus to cope with particles of a different size. Competition has often been invoked as the cause of macroevolutionary change. Although it is difficult to demonstrate, for example, some have suggested that post-Paleozoic decline in articulated brachiopods was at least in part influenced by the superior competitive advantages of bivalves that may occupy the same niche, and a similar argument has been made to link the success of dinosaurs with the decline of synapsids towards the end of the Triassic. One situation in which it has been possible to collect high-quality data concerns interactions between borers and skeletonized encrusters, for example, bryozoans, oyster-like bivalves and serpulid worms. These organisms have the advantage of having been preserved in situ, and thus the fossil maintain their spatial relationship to one another and to the substratum. It must be remembered that the soft-bodied encrusters, for example anemones, sponges, that may also have coexisted will be unrepresented, although evidences of their existence may be revealed by bioimmuration, preservation by the overgrowth of the skeletonized organism. In these cases, it is also possible to examine competitive overgrowth. It is known that space on hard substrates is at a premium in modern marine habitats, from which it may be inferred that taxa are able to rapidly colonize space will be at an advantage over those that do so less aggressively. Much of this type of research has been centered on two clades of extant bryozoans, the cyclostomes and coelostomes. Both evolved independently from soft-bodied ctenostome ancestors, the cyclostomes in the Ordovician and the coelostomes in the Cretaceous. The coelostomes replaced the cyclostomes as the dominant bryozoan clade, and it has been argued that the former were more successful competitors. An analysis of the competitive overgrowths between the two groups from a range of localities, that is Cretaceous to recent, by McKinney has revealed that coelostomes consistently won around 66% of all the interactions between the two clades. Although interestingly, this figure appears to have remained constant over geological time. Coming to the predation. All organisms die, and a great many deaths are the result of being eaten by the predators. Becoming part of the food chain, the need to avoid predation is a very important selection pressure. Hence, the battery of defensive morphologies, for example, spines and thick shells, behaviors such as leaping by cockles or swimming by scallops, such as paleoecologists, are not limited to exceptional preservation to chart the evolution of different predatory groups and methods. Various aspects of an organism's functional morphology, such as possession of teeth or claws, may suggest that it was a predator. For example, the large-toothed chelicera of the Paleozoic eurypterids, that is, large aquatic scorpions, have been used to suggest that they may have been powerful predators of the early fish. Most theropod dinosaurs, including the well-known Tyrannosaurus rex, have narrow, sharp-pointed, curved teeth, many with serrated edges, which suggest that they were carnivores. The most useful evidence, however, has come from the study of prey remains. Although some predatory groups ate their prey without leaving any evidence of the damage, for example, starfish that prize apart bivalve shells or fish that simply swallow their prey whole. There are two important and widely used predatory methods on shell prey crushing and drilling that can be recognized in the fossil record. A whole variety of arthropod and vertebrate predatory groups feed by crushing open the shells of their victims, many leaving very diagnostic breakage patterns. Similarly, a number of worms, gastropods and octopods drill neat holes in their victims for either the extraction of the tissue or the injection of the toxins. Where such damage is evident, it is possible to undertake quantitative surveys of the frequency of attack by a particular predator group and the frequency of the prey repair, which provides a measure of the effectiveness of their defenses, and also some aspects of the behavior, such as prey preference or stereotypic, predictable, and so diagnostic of the predator attack strategy. There is now a strong body of evidence to suggest that levels of predation pressures have increased during the Phanerozoic. Many bivalve taxa adopted new life habits such as cementation and deep burrowing, which can be shown to have decreased the threat from predators, and stalked crinoids moved away from shallow water communities into deeper habitats where there would have been fewer predators. Geologists apply the term Pangaea from the Greek words meaning all earth, and usually pronounced as Pangeo, to the supercontinent that existed during the late Paleozoic and early Mesozoic, about 300 to 200 million years ago. Pangaea was an amalgamation of the continental blocks that were the precursors of the existing continents. Through much of the Eastern Asia was an archipelago of islands loosely connected to Eastern Pangaea. Pangaea was accreted from the continental blocks that differed from today's continents. The southern supercontinent of Gondwana, also called as the Gondwana land, was the Paleozoic amalgamation of the South America, Africa, Antarctica, Australia, and the Indo-Pakistani subcontinent, as well as several smaller terrains. The northern supercontinent of the Laurasia or Laurasia consisted of North America and most of the Europe. Asia, however, did not exist as a single block. The continental nucleus of the present-day Asia was the Siberian bloc, but other blocks included Kazakhstan, Tarim, and a loose archipelago of the blocks that were to become much of the China and Southeast Asia. Many of these Eastern Asian blocks originated as silvers of the northern Gondwana and drifted northwards during the late Paleozoic and earliest Mesozoic to accrete to the larger Asian blocks during the late Triassic. Jurassic Pangaea was surrounded by the universal ocean called as the Panthalassa, from the Greek words meaning all sea, which was the ancestor of today's Pacific Ocean. The Atlantic Ocean did not exist even in ancestral form because of the fusions of the North America to Europe and of South America to Africa. An arm of Palaeoecology formed a deep east-west embayment in the eastern edge of the Pangaea. This was the TTC, which is named after the sister and consort of Oceanus in Greek mythology. Tethys was the ancestor of the present Mediterranean Sea. Successive ocean basins within it are termed as the Paleotethys that existed from Devonian to Permian, and Neotethys, the latter opened during the late Permian as a result of rifting between Gondwana and the smaller Central and Southern Asian terrains. The Pangaean supercontinent came together, that is accreted at the end of the Carboniferous when Laurasia and Gondwana were sutured along what has been termed as the Hercynian megasuture. The late Carboniferous was a time of the vast cold swamps in the tropical latitudes. There was a steep temperature gradient during the late Carboniferous from icy poles to hot tropics, which was more similar to today's world than perhaps at any other time in the Earth's history. In Gondwana, ice ages pushed glacial ice to within 30 degrees of the paleoequator. Once assembled at the beginning of the Permian, Pangaea stretched from pole to pole in a single hemisphere. The ocean of Palaeoecology covered the other hemisphere. Permian Pangaea was a relatively diverse place in terms of climate and topography. Permian glacial deposits found in South America, Africa, India, and Australia provides evidence of continuing glacial ages in southern Gondwana during the early Permian, late Permian, and Triassic. Intense mountain building and foreland basin deformation took place around the Pangaean margins during the late Permian and earliest Triassic. The maximum accretion or integration of the Pangaea occurred at about the end of the Middle Triassic, approximately 230 million years ago. Early Middle Triassic Pangaea was a much more cosmopolitan world than the Permian Pangaea. Indeed, the breakup of the Pangaean began in the western Tethys and severed the supercontinent into two pieces, north and south, by the Jurassic. The east-west rifting that opened up the Atlantic Ocean basin was not really achieved until the Cretaceous. Friends, today we have discussed broadly two aspects. First is the applications of the paleontological data in the paleoecology, and another is the paleogeography. The paleontological data in paleoecology has a simple meaning that the organisms that are benthic will live on the same floor where they are being deposited, and they will not be moving away from their place of origin or the place of death, and therefore they will give the information regarding that place only, which is not the case with the fossils which are planktic or move across the oceans. Therefore, for the paleoecological studies, only benthic organisms or benthic taxa should be preferred. And they give the paleoclimatology, the paleoclimatic inferences and paleoenvironmental inferences also. Then in the next part we have dealt with the paleogeographical models or the paleogeographical informations that we have received through our stratigraphical record. It says that the land or every piece of the crust today also, it is in a constant state of movement, and applying the principle of uniformity, that what is happening today had happened in the past. With this principle, we will know that the continental pieces are moving and have moved also in the geological past. So they have changed the paleogeography also, and that is why we have at times when all the continents were united in the form of Pangaea, and this Pangaea was broken and the continents started moving apart, changing the paleogeography of the earth. That was an interesting aspect to deal with. Maybe you like it. Thank you very much.